Is it time?
5 seconds you have.
No, I have 2 hours in 5 seconds.
You're on.
Okay, so let me talk about what I wanted to talk about this morning. I got distracted. First of all, again, please, if you have a question, stop me immediately, because there was an issue which I was asked about after the lecture, and let me explain this again, because I will be using this over and over. So let's assume that I have a Hilbert space H, and I have a function, say f, from a group into Hilbert space H. What do I mean by the integral f of x dx? I use this in writing all these formulas without too much comment. So the way this is okay, I'm sorry. This is a function in L of H, in operators in Hilbert space. This is, I can do the following. This is by definition, if I apply this V and put here V prime, this is equal to the integral over G f of x V prime dx. Here, this of course is a matrix coefficient of this operator valued function. So this is a function on the group. We can integrate this, and this function is a matrix coefficient of a well-defined bounded operator, which is a simple exercise to prove, and this gives the meaning to this integral. Of course, if you want, you can reconstruct integration theory starting with approximation with step functions, where it's clear what your operator valued integral is, but this doesn't make sense. So this weak formula explains what I had in mind, and this will be used over and over today in various forms. Okay, so what I want to discuss now is the construction of the category of Harishchandra modules. So let me start with, again, with the things we were discussing before. And if G is, say, compact, and we are considering finite dimensional representations, then basically finite dimensional representations are continuous homomorphisms of the group G in the general linear group of a linear space. And there is a fundamental theorem of Cartan which says that any continuous homomorphism of Lie groups is automatically differentiable, or actually real analytic. So continuity implies differentiability. Therefore, I can differentiate my homomorphism, and I get a homomorphism of corresponding Lie algebras. So in finite dimensional case, the attachment to representation of the group, representation of the Lie algebra, is in some sense automatic and very transparent. This, of course, fails miserably if we are dealing with infinite dimensional spaces. And so let me now assume that, say, H is a okay, let me give you a simple example. Let's look at L2 of R, and I can consider a unitary representation of a real line, which is given by, say, pi of t applied to f at the point S is f of s plus t, just the action by translations. And then if you look at the vector, which is represented by a function which looks like this box, and calculate its matrix, so for example, this is a vector v, calculate the matrix coefficients pi t v v prime, then you can easily see that this is a continuous function but not differentiable. So I mean, assuming continuity of representation doesn't imply differentiability of matrix coefficients. So if you have a representation of a Lie group on infinite dimensional space, you cannot easily differentiate. And this is exactly what somebody pointed out during Peter's talk, that there is an issue related to this, and this is the issue I want to address. I mean, related to construction of Harish-Chandra modules. So before going to this, let me get more specific and consider the situation in which we are. So we are looking at G is SL2R, and our K is this maximal compact we are all using, so cosine phi, sine phi, negative sine phi, cosine phi, and phi is real. And let's assume that H is a Hilbert space. And I think Bardman in his paper on representations of SL2R modeled that issue, the issue Peter was discussing about the behavior of the unitary representations of SL2R restricted to maximal compact. But I mean, in that time when, say, Harish-Chandra started studying representation theory, infinite dimensional representation theory of semi-simple groups, I mean, because of the interest in physics, people were studying unitary representations, and they wanted to understand unitary representations, and they wanted to use the methods of function analysis, like the tricks we were doing earlier with compact groups, and things were kind of failing or leading nowhere. So Harish-Chandra figured out what is the natural way to study the problem, and let me just briefly describe in this situation of SL2R his reasoning. So let me start with unitary representation and then representations, and then I will generalize the construction, because Harish-Chandra realized that unitary representations are too narrow for some reasons. So let's assume that on this Hilbert space, I have unitary representation pi of G. So this unitary representation is, as always, is continuous. So if I look at the function from the group G into pi G of V, this is continuous. And we can consider this representation and try to analyze it. So the first thing we remark that we can restrict pi to k. And as a representation of k, this can be decomposed as I described in the first lecture today. So our K has representations, let me call it tau n of cosine phi sine phi negative sine phi cosine phi goes to e to I n phi when n is an integer. So this is an irreducible representation. To any n, I can attach orthogonal projection Pn, which is obtained by taking the complex conjugate of the characters. So this is e to the minus n phi, and integrating representation with respect to this function. And what we get is an orthogonal projection from space H to a subspace I'll denote by Hn. And from the formulas I discussed this morning, but you can also check this directly, K acts on Hn by multiplication with tau n. So basically, our representation pi decomposes into Hilbert space orthogonal, Hilbert space sum of these subspaces Hn parameterized by integers, and on each space, the group K acts by this irreducible representation. So now let's assume that pi is irreducible. The first result Harishchandra proved in general theory is something remarkable, and this is related to the notion of admissibility Peter mentioned several times in his talks. So Harishchandra proved and I will state it for SL2, and then I will comment what happens in general, that so if pi is irreducible unitary representation, that the dimension of Hn is less than or equal to 1. In general, so if I look in an arbitrary semisimple group G and its maximal compact subgroup K, then Harishchandra's statement was that corresponding subspaces, isotypic subspaces for irreducible representations of maximal compact are finite dimensional. So basically, in general, you get a weaker statement that this is a finite dimensional space. And in this case, just this is essentially a fluke that you get that this is either trivial or one-dimensional. And this is specific for SL2. But the important fact, the dimension of Hn is finite. I mean, one can prove this, and I plan to prove it, but now because we are so far behind and everything, I won't prove it, because the proof of this in SL2 case is just a dirty trick, and it's not very useful to understand the situation in general. So basically what you do, first of all, I mean, this is, I won't really prove anything. I will just give you a small hint and introduce some notation which I will need later. If I have a unitary representation of G, then I can define, first of all, I can define the group algebra, and I will have several versions of this. So let me denote by C naught of G, smooth, okay, do I want to, no, yeah, let's assume just continuous, compactly supported functions. My group is non-compact, so Haar measure is infinite. I cannot define the convolution of arbitrary continuous functions, but I can do well with functions with compact support, and I have my convolution. So this is my group algebra with a convolution which is given by the same formula as in the case of compact groups. And then what I described a few moments ago, I can define the representation of the group algebra on our Hilbert space. Yeah. This is a good question. I have to normalize it and not change it, but basically, I have to keep track of normalization. This is the only thing. The natural, and you ask, so I really didn't want to go into this. This group algebra can be viewed, and this is a more orthodox way of looking at it, as compactly supported, say I could use the algebra of compactly supported measures on a group. And these, the function and this measure and the Haar measure are an example of such compactly supported measure. And this is what is natural. Here, to avoid too much fuss, I'm just going to fix a Haar measure. And if I want to get some explicit formula, like Plancherel formula, then I have to do what you want. I have to fix Haar measure because my final formula will depend on this. But in general, I can cheat a little bit. So this won't make too much difference in this particular case. Okay, so we have this group algebra. Does this answer your question? There was no answer, but so anyway, we have this unitary representation, and then we have a representation of the group algebra. Here, on my functions, I can, what are these projections? The projections are integration with respect to this e to I n phi. So these are like Fourier coefficients of our vector. So I can look at right and left regular action on my functions, and I can take functions which on left and right lie in the corresponding isotypic component determined by some n. And I get the subalgebra of this algebra. This subalgebra naturally acts on this space, H of n. And then the main trick is that by some mumbo-jumbo, which follows from Cartan decomposition, I can show that that algebra, in the case of SL2, is commutative. So I will get an action of commutative algebra on this space, and from this I can conclude that the space has to be one-dimensional, because I conclude also that because the representation pi is irreducible, the representation of this space has to be irreducible, and then I'm using some analog of Schur's lemma to establish this. In general, this argument fails, and you can do it only if this n corresponds to the trivial representation of k. So in this parametrization when n is equal to 0, so you can show in general that if you have irreducible unitary representation of G, then the space on which maximal compact acts trivially is at most one-dimensional. For SL2, you can do it in general. So this is one remark which takes care of some things Peter in his calculations just assume as facts. Okay, so now there is another issue which is important, and this, yeah. I take compactly supported functions which transform on left and right under the same representation of k. And this acts on isotypic component. I mean, you have to be careful how to define is it n and minus n, so that it acts on this space. Okay, so now let's discuss the issue of differentiation. We said that matrix coefficients, so if I look at a function g into, okay, let me take say x into pi x of v is not differentiable in general. But we can do the following trick. We can just make this function differentiable by taking, so if I take this vector v and on my group, so I look at my group, I look at the neighborhood of identity, and I look at a compactly supported smooth function which is supported in some neighborhood of the identity. And I can apply this. I can look at the integral and look at, let's say, this is some function f, pi f, pi f of v. So this is the integral over g, f of x, pi x of v dx. And now I can shift this by, say, some pi of y. So if I do this, I will get pi of y here. Then again, higher measure on SL2 is bi-invariant. I think this is what Bill mentioned in his talks. You can easily check this. So what I can do, I can change the variable, and I have multiplying by pi v generates here a shift by y inverse. And now I can differentiate this with respect to y, because here I have a function, so I take f to be smooth.
Excuse me.
Yeah.
So why can pi
this is this integral by definition. And I mean, this is continuous, compactly supported, actually smooth, compactly supported function. This is continuous vector valued function. So this is an expression which is continuous with compact support, so I can integrate it. Agree? Yes. Okay, good. So now, you see, now we can differentiate this because this is a smooth function. It has compact support, and we can write down estimates, and if we are diligent enough, the derivative exists. One can show this, and just because f is smooth. So since f is smooth, this pi of f v is a differentiable vector. So we say that, say, v is a differentiable vector if the function x into pi x of v is differentiable. And I remark in this example, you can show that in general, not all vectors are differentiable, but now I gave you a sketch of the argument that there are some differentiable vectors, and these differentiable vectors are dense because, you see, I can construct such a compactly supported smooth function such that its positive and its integral is equal to 1. And also, I can do this in such a way that I basically can make the support around identity as small as I want. So if I take such a I take my group, I take identity, okay, I put a metric in here, and I take supports into in balls of radius, say, 1 over n, I get a sequence of these smooth functions fn, and if I apply a pi of fn to the vector v, then a very simple estimate shows that this sequence converges to v. All these vectors are differentiable, and this v is completely arbitrary, so we see that differentiable vectors are dense. So this is the first remark, that we can define these dense differentiable vectors, dense subspace of differentiable vectors. And this subspace shows the perversity of infinite dimensional representations, because clearly the space of differentiable vectors is invariant under the group action. But it's also dense, so irreducibility in algebraic sense doesn't make sense. We really have to look at closed invariant subspaces. It's very simple to check that if I take a differentiable vector and apply this projection, I will get a differentiable vector. So the conclusion is that I have a dense subset, a subspace of differentiable vectors in H. I project them into Hn. I get something dense again, but Hn is, either zero-dimensional or one-dimensional. So basically, I get everything there. So the conclusion is that Hns consist of differentiable vectors. In particular, the algebraic sum of all, so this denote the algebraic sum of all HNs. This is the object on which Peter was doing calculations, consists of differentiable vectors, and on those vectors we can take, say, pi exp t of some element of Lie algebra x applied to V. This is the differentiable function. I can differentiate with respect to t at t equals 0 and define that this is pi x of V, and I get a representation of the Lie algebra. So this algebraic sum is definitely a module over Lie algebra, and of course on it representations of K act, because this is algebraic sum of representations. Okay, so this is an example of GK module. I am still discussing just example, so I will make a precise definition in a moment. Okay. Still, we want something stronger, and I spent some time discussing these details because I would like to know that knowing Harishchandra module, I can say something about representation of G. So for example, what does it mean knowing representation of the Lie algebra? This means I know how these pi x's act. I can extend this representation of the Lie algebra to the representation of, say, complexify Lie algebra first, and then a representation of universal enveloping algebra, what Peter was discussing, and I get U of G action on H, on this algebraic sum of HNs. So now let's assume that our vector is not only differentiable, but real analytic. I mean, let me remind you, real analytic means that the vector is infinitely differentiable, but also the Taylor series at each point converge in certain neighborhood. In this case, I can look at this. So if V is an analytic vector, then for small t, so for small t, we have the formula that pi exp t of x is equal to the sum, n goes from 0 to infinity, 1 over n factorials. Okay, let me put t to the n here, pi x to the n applied to V. Oh, I lost my vector V. So this is the meaning that the vector is real analytic. And then Harishchandra proved that not only that the vectors in here are differentiable, but they're actually analytic vectors. So let's see, can we modify this proof to, yeah?
In order to know that each k-type is finite dimensional, we use the irreducibility of the GK module.
Yeah.
Right? But for the very existence of the GK module, you seem to be using the finite dimensionality of the k-types.
I mean, let's assume that pi is, I didn't define anything yet. So I can assume that pi is irreducible.
Yes, but pi being irreducible, I mean, I'm saying that in order to know that each k-type occurs with finite multiplicity,
yeah,
you are assuming that the GK module is an irreducible GK module.
No. No, no. I mean, the proof of this theorem is completely, has nothing to do with the action of Lie algebra.
Even for general groups?
No, for general, I mean, in general case, the proof is different, but the proof I was describing for SL2 is exactly what I said. It uses algebra. I just made a statement about general. You will see till the end of this mini course, you will see several, maybe 3 or 4 different proofs of the same statement, which work in general. This is why I didn't want to do this proof, because this proof is a fluke which works only for SL2 in this generality. So in general, what you are saying is correct. That one has to be more careful, but here I'm just discussing SL2. Okay, so how can I of course, this is the idea of the proof, if I can generalize this, modify the construction of this delta sequence, Fn, of my bump functions to be real analytic, then I will get density of analytic vectors. But can I construct an analytic function with compact support on the group? So Rishi is not happy with this idea. Yeah, this is a physicist's proof, which is false. If you have a real analytic function, that this real analytic function, the best you can hope that it will decay rapidly in infinity, and you can construct this. For example, you can do something like, on a real line, you can use, say, I don't know, n squared, x squared, and here, put n and divide by pi, something like this, what you can easily check, will give you the functions with integral equal to 1, where as n grows, they're kind of shrinking around the identity, so which will give you your delta sequence. On SL2, you can construct, because your A is isomorphic to real line, and your N, shows you in Kasselman's lecture, is also isomorphic to real line. You can write functions like this there, and then fudge stuff on K and construct your delta sequence explicitly. Harishchandra did this in general in a very complicated way, but later there was a nice proof, which of course requires more work, and this is looking at the heat equation on the group. So you take a heat equation on your group, and you know this function, something slightly different of this, but related, is a solution of heat equation on the real line. And in general, if you look at the heat equation on the semisimple group, you have a rapidly decreasing a real analytic function on the group, and you can use this to form this delta sequence. Of course, I am telling you all this story, which is just because of one reason, just to point out that the issue is tricky, because your function, when you are proving density of analytic vectors, your function is rapidly decreasing. And therefore, you have to know, for unitary representations, this is okay, because your matrix coefficients are bounded. Because, it's a unitary representation. So if you have a rapidly decreasing function and multiply something bounded, the integral converges. So this thing is well defined. Yeah?
Is it true for any analytic manifold that you have a delta sequence of analytic functions on it?
I have no idea.
Okay, that will be.
I mean, or an arbitrary analytic manifold. Do you have a delta sequence of analytic functions? I mean, it's a global question, so it is. I think I am not an analyst. Yeah, even, but I mean, Lie group is very simple topologically, and so the reason why I wanted to point this out is actually related also to a question, because we want to generalize the construction. I mean, Harishchandra observed that when you have this algebraic construction, if you remember from Peter's lectures, he was writing down the action of the Lie algebra and constructing various modules. Some of those modules correspond to unitary representations. Some of them are not unitary at all. So Harishchandra said, okay, let's generalize the construction. And when you do this, you can do it in a lot of different ways, because definitely whatever you do, you will lose the results I stated here. So he defines, say, let me assume that, say, X is a Banach space. So pi is an admissible representation of G on X if, I mean, of course, we take the same definition of continuity if X is Banach space sum of xn's, n goes over Z, and dimension of xn is less than is finite. Of course, I mean, here by this I mean that you take algebraic sum and just take the closure, because of course there is no canonical Banach space direct sum. So this admissibility is for irreducible unitary representations. It's a theorem. Here you take this as a definition, and then you can show that if you have a Banach space representation of the group, the norm, the growth of the norm, will be bounded by exponential function on the group, and you can match the growth by the decay of your delta sequence, so you can prove the density of analytic vectors. And again, in this case, you also have that algebraic sum of xn's. So, okay, I know it. Is a module for enveloping algebra and for K. So this is how Harishchandra introduced this notion of admissibility, and and the reason for this was to replace this theorem for unitary representations by a definition. One can show that there exist irreducible Banach space representations of, say, SL2, which are not admissible. So this is a real restrictive condition. Okay, so now let me define precisely Harishchandra modules. So what is Harish-Chandra module? So the pair pi v is a Harish-Chandra module. If first it is a U of G module, second, it is an algebraic sum, I mean a sum, but let me just stress of isotypic subspaces say Vn, which transform with respect to tau n. So I mean, this is just the labeling. So I can write V as the algebraic sum of Vn's. And of course, here on each Vn, the group K acts by tau n, so I can differentiate it. And if I denote by K the Lie algebra of the group K, then on Harish-Chandra module, the action of this Lie algebra, which is obtained, the action of the element, I think, Castleman denoted by X, which is obtained by differentiation of the group action and the action given by the same subalgebra sitting inside G, they're equal. So this is this compatibility condition. K, there are two actions of the Lie algebra of K. First of all, Lie algebra of K lives inside the Lie algebra of G and inherits its action. The second thing is the group K acts, and of course this is a direct sum of one-dimensional representations. You can differentiate this, and you get the other action, and these two actions have to be compatible. Yeah.
Differentiate that representation, you get the same representations exactly.
Yeah, exactly. Yeah, yeah. But you see here, this makes perfect sense even if there is no underlying representation of G. This is just the module for two different actions which are compatible. And then, of course, you can define morphisms between Harish-Chandra modules in a natural fashion. So if I have two Harish-Chandra modules, pi v and say n and w, then if I have a linear map from v into w, which intertwines the actions of the enveloping algebra and the action of K, that this is a morphism of Harish-Chandra modules. Yeah. I mean, it's the same thing. We are not really, I mean, if you look at the literature, you will have infinitely many definitions. And I think I will probably, when I talk about D modules, I will probably use a slightly different definition. Sometimes you can drop, if you want to do homological algebra, you drop the finite dimensionality of Vn's. If in some cases,
They were not there to begin with. There's no finite dimensionality.
Okay, I actually, yeah, I even didn't put it, but I wanted to put it. So yeah, let me put here now dimension of Vn is finite. I mean, sometimes you want to assume finite generation as a U of G module. So it's basically you want to have irreducible objects which will have all of these properties. Depending on the situation and type of argument you are doing, you can change this, and we are going to do this differently in different situations, as you will see. But let me just, because again I am getting close to the end of the hour, point out some things. First of all, let me point out that we have a natural functor, say if pi h is, say, irreducible unitary. I mean, this is stupid category, so let's, if I look at this, I can go to corresponding Harish-Chandra module, and this is well defined. If I'm looking here, say, I can define a category of admissible representations. For example, take my Banach space representations with these properties, define morphisms as continuous maps, so intertwine that, and then I get corresponding Harish-Chandra modules, and so then I have a real functor. But going backwards is very obscure, because if you take a Harish-Chandra module, you can have infinitely many wild topologies in which you can complete your Harish-Chandra module, extend your representation, and get a group representation. If you look back at the modules Castleman was looking at yesterday, their core, the Harish-Chandra core in those modules were always the same, but choosing different classes of functions, you were getting different completions. And you have to be really careful when you do this, and there are maybe, Bill would probably pick a different class of function analytic objects instead of Banach spaces to discuss this issue. But I want to emphasize that there are some functorial completions, and we are going to talk about some of them at least. So there are some functorial ways to go back, but definitely why there is essentially one way of going from representations to Harish-Chandra modules. Going back is much trickier, and this shows why this algebraic version of the problem studying Harish-Chandra modules has preference. At least this was the way Harish-Chandra attacked the problem. He studied the properties of Harish-Chandra modules, and then he proved a theorem which is very actually simple to prove. If I have a Harish-Chandra module and I have an inner product, and this inner product satisfies obvious properties, so that the representation of K, or the maximal compact, with respect to this inner product is unitary, that the representations of a Lie algebra, so if real Lie algebra is given with, by anti-self-adjoint operators, then if you take this inner product, you complete your Harish-Chandra module with respect to this inner product, then you get a Hilbert space, and you can exponentiate the action of the Lie algebra to this Hilbert space, and you get a unitary representation. So this, we call such Harish-Chandra modules infinitesimally unitary. And if I have an infinitesimally unitary Harish-Chandra module, there is a unique unitary representation on the other side which corresponds to it. So you can solve this classification problem of unitary representation by purely infinitesimal methods. And here, the critical trick in constructing this and uniqueness of the completion is the fact that these vectors in Harish-Chandra module corresponding to group representation analytic, and this is something I'm going to discuss when we discuss matrix coefficients tomorrow. Another thing which I should mention earlier, but I didn't, is it was not, I think, completely clear why analyticity is so much better than differentiability. So let me finish by looking at the following situation. Let's assume that X is admissible and so this is an admissible representation of group, and inside this I am looking at the corresponding Harish-Chandra module xk. We usually call this xk space of k finite vectors because each of these vectors, because they are algebraic sum, under the action of k spans a finite dimensional subspace. So now you can ask, what are invariant subspaces here, closed invariant subspaces? They are in one-to-one correspondence with invariant subspaces for Harish-Chandra module structure in HK. And the reason for this is the fact that all the vectors are analytic, because if I have a subspace which is analytic, which is invariant under the action of the corresponding action of the enveloping algebra, I can take a linear form which is vanishes on this continuous linear form which vanishes on this subspace. I can look at Taylor series of the corresponding matrix coefficient, and the linear form will vanish on all the coefficients, and because of the convergence it vanish on the corresponding matrix coefficient. So you get that this linear form will be orthogonal to the closure of this subspace, which is group invariant. So basically, if I take a closed subspace here, I attach to it yk, which is xk intersected with y, and I'm going back, I can reconstruct y from yk by taking the closure operation. So the fact that all k finite vectors are analytic gives us that there is a nice correspondence between closed invariant subspaces in our admissible representation and invariant subspaces in Harish-Chandra module. Therefore, if I define irreducibility for Harish-Chandra modules just as the non-existence of non-trivial invariant subspaces, then I get irreducible module here corresponds to irreducible module in admissible representation, where irreducibility here is defined using closed invariant subspaces. So in a way, this is, this shows, gives you some rough idea why analyticity was really critical in this arguments for. So, okay, so my time is up. Yeah. I mean, this thing here, I mean, if I have a Harish-Chandra module which is infinitesimal, the easy way? I mean, here, this is admissible, so I have the space of all k finite vectors, the algebraic sum of all of this subspace is transforming with respect to irreducible representations of k. This space consists of analytic vectors, so it has a structure of a k module over enveloping algebra, so it's over there. So I'm taking a representation, taking all k finite vectors living in it. Does this answer your question? Because the proof I did for unitary representation works in this case too. Because if I'm dealing with Banach space representation, the representation when you go to infinity increases exponentially, but it increases slower than the solution of heat equation decays. If I take some perverse locally convex space, this argument will fail. So this is why I assume that this is Banach. And I mean, it is a tricky issue, and there are other ways to avoid this when you are dealing with completions. And this is definitely not a functorial completion. So Banach spaces are just, this is how Harish-Chandra look at this, and historically they play the important role. Any other questions? Yeah. Yeah.
You said that it had something to do with analyticity. You said something. You said the idea.
Yeah, I mean, from analyticity, it will follow that this is unique.
The completion is unique. No, the completion is.
I mean, no, the completion, but the action of the group. How you define the action of the group? You can write. So you will write sum n goes from 1 to infinity, say, this is infinitesimally unitary, so I take pi n of x applied to v and v prime divided by n factorials, and I want that this is pi of x tx v prime. But of course, to claim this, I have to know that this thing is convergent. So this is how analyticity enters the game. I mean, I will talk more when I talk about matrix coefficients about this issue. But I mean, this is another point where analyticity is critical. I mean, you see, this is, I think now you are really discussing things what we are going to discuss tomorrow. You can define the notion, I mean, Castleman also in his talk mentioned this. You are going to, we are going to write down differential equations for matrix coefficients. The identity of the group, these differential equations will have a regular singular point. So from classical Frobenius theory, you know that if you have a formal solution, that formal solution will be convergent. And the formal solution is just given by Taylor series. So enveloping algebra gives us a formal solution. This formal solution, because we are dealing with differential equations with regular singularity, is convergent. And therefore, we have matrix coefficients. I mean, this is roughly speaking, a part of the story for tomorrow, that from Harishchandra module, you can define matrix coefficients even if you don't know that the Harishchandra modules comes from a representation of a group. But I think this is the closest answer to your question. Any other questions? Okay.